Excellent. So hi, everyone. This is a quick look at the new P2 industrial module, or stamp module, some people might call it. It's designed to plug into one of these PLC. This is an 84-pin version of a PLCC socket. Hopefully you can see my screen share. I didn't ask, but I assume you all can. The idea of this module is to provide the most bare bones and compact module possible that system builders can use to put into their products. So it's a little bit different from the edge concept, which is more of a ecosystem for designing or engineering your code. This is what you would then possibly put into an end user product if you were building things. And so as a result, it doesn't have any of the extra things like serial port interfaces, USB. It's just bare bones what you need to run the chip with your own software. So that's the concept. The layout is quite similar to the Edge. And maybe that's a good way to kind of work through this, just to explain what we've got here feature-wise, sort of comparing it to the Edge in terms of what we've changed. The main changes, we sort of started with the Edge module design, and the main changes really were just making everything smaller, because obviously this thing is small. So it's got a smaller, I'll start at the top right, it's got a smaller crystal, but it runs with the same precision, 500 parts per billion. It's got smaller LDO regulators, these little blue dots. They are similar in performance to the previous ones. Well, slightly better because they're newer. So slightly lower standby current, slightly higher possible current delivery, slightly lower ripple and stuff, slightly better line regulation. But they're essentially the sort of same size package size, but without the legs. So these are just using the BGA, solder ball format. So it's easier to squeeze them in. I've still got them out as sort of as far away from the P2 chip as I can, just to keep the heat path out towards the module edges, because these are obviously, and the reason that we use 8 like this is to distribute the heat load around the board as much as anything else. So yeah, so that's why they're sort of out on the sides there. We've got a couple of resistor nets here just to allow some settings. I'll show you those on the schematic in a minute, but they essentially replace the dip switches, because again, I think for system builders, you want to set your settings once and forget about it. There's no messing around with dip switches. And then down on the left-hand side, we have 2 banks of switching power supplies. They're both 3 amp power supplies. One delivers 1.8 volts to the PT core, the other P2 core even. The other one delivers 3.6 volts, which goes into the LDOs to produce the 3.3 volts out to each of the ports. So that's your 2 switching regulator setups. And that's really it. In the middle there is the big flash chip. We quickly realized that this project was going to be all about the size of the flash chip, because the dies on those things are pretty big, but that's the smallest package I could find. It's a 4x4, and that keeps the 16 megabyte capacity. So that's in there. And really, that's all. On the back, I've printed the there should be a button to flip this into reverse. Well, we'll just manually tweak that around. There we go. Come on. Chook, 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 chook. Yeah, so on the back, we've just kept it completely flat. So we want to try and do this so that people can easily bolt a heat sink or fan or something on the back if they want to. So this will actually be an exposed plated area, not blue as it's been rendered by this 3D model. And here's the specs: 8 cores, up to 300 megahertz we're going to shoot for. And that's really down to the thermal characteristics. 16 megabyte flash, as I mentioned, and the same high precision clock that we had on the Edge module, 500 parts per billion. Let me just flick that back round to the front. There we go. Yeah, so
Michael, Michael, can you flip that thing around again?
Yeah, absolutely.
Okay, that's good. That's good right there.
You happy with it that way around, or do you want it rotated? I mean, the last thing I wanted to mention, so if as we're here, maybe I just do that. Although this 3D render is upside down, so that's annoying. These two sockets were just examples. One's the lower profile one is an SMT socket, and the other one is a through hole. I suspect we'll probably aim to stock both at Parallax, but these are generally available as well. And I still need to try and ideally find an SMT part with holes in it as well, because this might provide quite a nice cooling path. There's a few options for cooling. Cooling shouldn't be necessary if you're running it, at regular speeds. But as always, people like to overclock these things, so it's good to kind of have that half in mind as we design these things. And we're going to, with this, we're thinking of bringing out a small kind of engineering development board or an engineering kind of example circuits board, which will have the socket and some basic circuits on it, so you can sort of plug it in and get going. And we'll have standard mounting holes around this socket, so you can fit a standard sort of CPU fan, whatever size it turns out to be that's appropriate for this module. And then you'll be able to bolt that either on the top side or the underside of the breakout PCB and experiment. And with the holes in the bottom of the PLCC socket there, that will allow the airflow to draw the heat off the bottom of the chip, because it's worth mentioning or reminding people that don't know that most of the heat comes out the bottom of the P2 chip rather than the top. So the bottom is really the sort of best place to try and get some forced air onto the thing. So yeah, if we design the baseboard with a cutout maybe that's suitable for a fan to blow, to pull the air through, but equally maybe on top as well, these holes in the socket will allow air to come through. There are some small spaces in the socket, so it'll have some offset from the board itself, so it won't present a completely sealed in terms of airflow. It won't present a sealed design, so that you'll be able to add a fan either side and get airflow over the thing. So that's the sort of idea there. As I say, it's not going to be necessary for most low speed or moderate speed products. A couple of 100 megahertz is certainly not going to be thinking about cooling. But if you're pushing it 300 megahertz direction, then you might want to add some cooling, especially if it's in a sealed a sealed package or a sealed box. Then you might think about some forced air cooling of some sort, or at least a heatsink. So yeah, that's the module. Chip, did you want to add anything to that? You mentioned you were thinking about something on the back.
Yeah, well, okay. Can I be heard now?
You're heard.
Okay, cool. So these are heat pipes, right? Little vias that go right under the metal pad of the chip, and their purpose is to pull the heat off of the chip, which sits on the other side of that metal pad that is soldered to the other side of this board. So you could do something where if you took, oh, by the way, this is something another customer made. This is the same size, same form factor. This has a lot more circuitry on it. But this had a P2 here, and so he had like the heat area down here. If you were to mount something like this onto a board, let's say you had a big square cutout, you could put oh yeah, here's the socket size incidentally. You could put a heat sink, like a self-adhesive one, just on, if this is cut out on the motherboard, right, that this thing goes onto, you'll have room to just stick a heat sink there, which would help with the heat dissipation. Because you know that in this, in the regular P2 Edge, we we went through a lot of iterations on this to get the heat dissipation. So we have all those heat pipe vias back here, and then this is like a heavy copper plane. We had the PCB guys make it thicker so that it can spread the heat a little better. And that enabled this thing to run at like 340 something megahertz. So this, of course, is going to have less area to dissipate. So it's, it's going to get hotter faster. But there are things you can do in your implementation to fix that, like put a heat sink on, or maybe a fan, which I'm not a fan of because that's like more heavy moving parts. But anyway, so this is the form factor. It's pretty small, and we'll be able to sell this in volume for 29 bucks, and then in lower volume like 39, because the P2 Edge that we have, this is like a good place to start if you're just starting to work. But the connector for this thing is like volumetrically larger than the whole board, and then if you want to make it flat, well, then you got a right angle connector, which you can get, but it's going to stick out, and it's going to still be more volume than just this thing. And in some applications, hey, Josh, you want to hold up one of your guns? They want a tagger, yeah. They want to put P2 into that thing, but they cannot fit this. And we put a lot of effort into making this whole thing. I mean, getting all this stuff. This is like the 4th or 5th iteration, and we finally really got it dialed. And this is a 6-layer PCB. So to just implement the chip isn't trivial because of the heat matters, and you got to keep the impedances down. And the reason also we have these regulators all the way around is not just for heat dissipation to spread the heat, because they're only dropping 0.3 volts, right? But also it provides little quiet islands for each set of 8 I/O pins, because the pins have ADCs in them and DACs. So it allows you to do quiet analog stuff on every group of 8 pins. So anyway, this will definitely fit in their taggers. Oh, yeah, James.
Yeah, so you've done any testing as to whether the module will stay in the socket reliably and make good electrical contact?
We're going to be there soon. Oh, okay. Okay, James asked, have we done any testing to know that this thing will indeed fit the socket well and not like wear out the contacts and all these kind of matters? So no, we haven't yet, but this guy went through some special PCB process. Maybe we'll have this up here if someone wants to come look at it later. These are castellated edges, and there's some kind of special like metal forming and plating process that puts what might otherwise be like the interior of a hole all along the side. So this thing is 84 pins all around, so it's got 21 per side. And it's very much, I don't know how thick that plating and metal are, but it's sufficient. It'll go into the socket, and I think if we can just get the dimensions right, we should be fine. Looks like it's kind of sensitive to the corners. Maybe we need to like chamfer the corners a bit to get them to fit in here, because this one actually isn't really going into the socket because
hold it up to the camera here.
Oh, sorry, yeah. So here's the socket, and then here's the module. So we're going to have to like put right angle cuts on those corners so that it will clear the socket. Oh, okay. So, oh yeah, the other corners do have cutouts. Okay, so yeah, it will go like, let's see, which is the beveled corner? It looks like, is that one it? Yeah, sure. I think
there might also be a dot for pin number 1, which will be
I don't want to poke it in here because I'm not going to get it back out. It's going to be really tight. But this could be mounted on a socket or just soldered, onto a board with a surface mount process.
Michael said there might also be a dot indicating pin 1.
Oh, there is. There's a fiducial mark. Yeah. Oh yeah. Look at it.
So questions for,
because on these sockets, the pin number 1 is actually halfway along one of the sides. So it might be dotted, and on the socket you'll see a little triangle or a marking on the socket as well.
the quiescent current of the switchers. What we can do, because we have 84 pins and we only have 64 like signals and we have power and grounds, we can put some control signals. I believe the switcher Michael is using has some kind of power down thing. So we'll be able to use those extra pins to shut those things off. And then how to turn it back on, I don't know, maybe you need an external event to hit a PFET or something, or maybe an RTC to create a timer event to turn it back on. And that can all go, you know, onto a little motherboard. And because this thing is so tight, you know, we have some versions of this. Well, you won't see the difference from here, but we have little.
Go ahead and hold it up to the
Okay.
camera, and that'll zoom you in on the.
Yeah. Here's our 32 megabyte version, right? So it has these 4 super tiny little parts that have right up here that have 8 megabytes each. But because that socket thing is so tight, we could actually just put those on the motherboard that it goes onto, and we're only going to pick up maybe another centimeter of trace. It won't be bad. I mean, on this one, we have like, you know, very, very, very short leads because that thing's running at, I think we can clock it at like 100 and, well, half the clock, maybe 150 megahertz it runs. So, you know, that's pretty high frequency. So you need very short traces.
I could actually
Any
say
other
something about
questions?
you can't really go as low power as possible because of the clock.
Yeah, we're going to have some kind of control input because the schematic is going to change a little bit before this is done. And so we'll have to shut down that TCXO that's 20 megahertz, and we'll also have to shut down the regulators so that the quiescent current can go just to that. That'll take all that other stuff out of the circuit. Then we'll just have the leakage of the well, no, actually it'll shut off the P2 completely. So we should be a few microamps, I think. Just about to 0. And then for running at low power, maybe Michael can comment on what the quiescent is on those 2 switchers, because if you're running the P2, you're going to have the 1.8 volt and the 3.6 feeding those LDOs to get everything alive. And then you can run it off the internal RC oscillator at 20 kilohertz. It'll take very little additional current, but there is on the P2 itself, I think, there's some leakage when it's on. It's maybe like 400 microamps because of probably mainly all the SRAM arrays. They leak a little bit, and when they're powered on, they're just going to take some power.
Did you want to have Michael comment on that?
Yeah.
I don't recall offhand what the leakage is of the switcher in standby, but it'll be, you know, single digit microamps for sure. I can check it in a moment. The other thing that just going back to what you mentioned about spacing or lead or trace length rather, that's something I'm sort of still you know, in flux about which way to go best. But as it stands, with the image on screen, I've got the top bank of IO pins, if you like, and the bottom bank of IO pins. So this is P03, P0 is down on this bottom left at the moment. So we've got the top and the bottom banks are 5 millimeters away from the pin edges, all equidistant. And then the right-hand side pins are 2.5 millimeters away. So if you really wanted to have some super fast stuff, you might consider putting them on the right-hand side, although arguably not the 4 near the oscillator, but certainly the others down here. But top and bottom, they're all equidistant as well. And, you know, 5 millimeters is probably not a concern for most applications, as long as you know, even if you're running data, if you run your clock line slightly longer, you're not going to have an issue with 5 millimeters, I suspect, even for high-speed data.
Did you intend to share screen?
So we're going to move on to the next presentation.
Okay, so.
Any final questions for Jeff? Okay. Okay, grab your computer.